Hi there, and welcome to Chapter 4.1, The Basics of Probability, in Stevens' Introduction to Statistics, the Think and Do book. And here we're going to go over some terminology, and then we're going to define the classical approach to calculating a probability. And we'll do a couple of other approaches, but that's the main goal of this particular chapter. And instead of starting with these definitions and notation, I'm going to start with the down here, the example. Alright, but before I do that, I'll go into full screen mode. Okay, so here's the example I want to discuss. Suppose you flip a coin, or you're going to flip a coin 2 times, and I want to calculate the probability of getting 1 head and 1 tail. So that's the probability. What's the probability before I start flipping that I get 1 head and 1 tail when I'm done with this? Okay, so now I'll go back to my terminology. It'll make more sense if I can describe these things in the context of a problem. Okay, so the first thing we start off with, an event is any collection of results or outcomes of a procedure. And in our case with the coin toss, the event of my concern is getting 1 head and 1 tail. The procedure is flipping the coin twice. A simple event is an outcome that cannot be broken down into sub-outcomes, right? For example, with the 1 head and 1 tail, that can actually happen in 2 different ways. You can get a head, then a tail, or you can get a tail, then a head. And those are 2 simple events. The sample space consists of all possible simple events, right? And then these notation, the capital letters, these will denote, A, B, and C, and capital letters like that. Those will denote specific events. And this thing, P parentheses A, that's P of A, and that will denote the probability of an event A occurring, right? And that's what we're trying to calculate. We're trying to calculate P of A. And a probability is a number between 0 and 1. Right? It can be 0. If it is 0, then the event is certain not to occur. And if it is 1, then the event is certain to occur. And the complement of event A is denoted A bar. Right? Everything that is not A is included in A bar. So all of the events that, or all of the simple events that don't make up A bar. So the classical approach to probability, and this is everything sort of falls back on this. We have formulas and variations, but they all really come back to the classical approach to probability. And the way you do this is you calculate the number of ways that your event can occur, and you divide that by the total number of events. Right? And if we call S the number of ways an event can occur, and N the total number of different simple events, then the probability of that event happening is the ratio, S over N. Okay, so we'll go back to our coin toss here. We're going to flip a coin 2 times. What's the probability of getting 1 head and 1 tail? Here the event is getting 1 head and 1 tail. But there are 2 simple events that compose this event, right? They are, say, a head on the first and a tail on the second flip. And then the other event is a tail on the first and a head on the second. So there are 2 ways that my event can occur. In this case, S equals 2. The sample space consists of all possible simple events. And we can get a head on the first and a tail on the second. Head on the first, head on the second, tail on the first, tail on the second, a tail on the first, head on the second. So the total number of outcomes is 4. So there's the 2 important numbers, S and N. And we'll denote our event getting 1 head and 1 tail. That'll be event A. And so we're seeking the probability of A, which is just S over N. In this case, 2 over 4, which is 1/2 or 0.5, right? Whichever way you want it. And specific notice, it's between 0 and 1, right? If you ever get a probability that's less than 0 or greater than 1, there's been some sort of error made. And now let's take a look at A bar. A bar, all right, is the complement of A. And so if A is one head and one tail, then A bar is two heads or two tails. In other words, A bar, the list looks like this. You can get head, head, or tail, tail. And so the number of ways that A bar can occur is 2 over the total number of different simple events, 4, which is 1/2, right? And here's the thing to notice. The probability of A does not always equal the probability of A bar. That's what happened here. That was purely coincidence. What is true, the relationship between these two things, is they always add up to 1. The probability of A plus the probability of A bar equals 1. And another way of writing that is the probability of A bar is 1 minus the probability of A. So A bar, again, is the complement. So the probability of A not happening is 1 minus the probability of A happening. And that should be intuitively sensible to a certain degree. And we'll get into exactly why that is later. Okay, so here we're going to do a your turn. In this case, you flip a coin 3 times. I want you to find the probability that you get the following number of heads given here. Right. What's the probability of getting 0 heads? What's the probability of getting 1 head, 2, 3, right? And so to do this, we create something that is sort of helpful for our purposes in these matters. And I'm going to create what's known as a tree diagram. Right? So this is the tree diagram right here. Tree diagram. And so the way you sort of do this, and we don't do a lot of this in this book, but you do your sequence of events, first flip, second flip, third flip. And on the first flip, you have 2 options, a head and a tail. And then for each one of those options, after you get a head, you get a head and a tail. After you get a tail, you get a head and a tail. And then from this head, you go head, head, and a head and a tail. And so if I follow this branch of the tree, that is a head, head, head. If I follow this branch of the tree, that is a head, head, tail. That's what I'm getting here. So I follow each one of these branches, head, tail, head, right there, head, tail, tail. And you go through that until you get all the way down to here, tail, 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 and that's the bottom branch. So what I have here on the right hand side when all is done is a list of all my outcomes, right? That's what's great about the tree diagram. So this table over here becomes very easy to calculate. What's the probability of 0 heads? Well, that only happens here. That's the only outcome where I have 0 heads. And there's a total of 1, 2, 3, 4, 5, 6, 7, 8. 8 outcomes. So there's 8 outcomes. Right, so the probability of getting 0 heads is 1 over 8. Move on to the next one. Is the probability of getting 1 head. Well, that happens in a few different places. There's this head, tail, 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 head, tail. That's 1 head, right? And tail, tail, head. Each one of these has 1 head. So the probability of getting 1 head is 3 out of 8. And that's where this comes from over here. Likewise, if I'm looking for 2 heads, I just go here and I count up my 2 heads. There's 2, there's 2, and there's 2. So that can happen 3 different ways. So again, the probability of getting 2 heads is 3 out of 8. The probability of getting 3 heads, that only happens in 1 way, and that way is right here, head, head, head. So that probability is 1 out of 8. Right? Easy peasy. Okay, your turn. 2, the second one. You win a lottery by purchasing one of 200 tickets. The organizers randomly select one ticket for a grand prize and 5 other tickets for small prizes. So the first question here, what is the probability you win the grand prize? Well, there's only one grand prize. There's only one way to win it. They draw your ticket, and there's 200 different outcomes. They could draw any of the 200 entrants. So 1 over 200 is 0.005. And that's the probability that you win the grand prize. What is the probability that you win a prize of some sort? Well, there's the one grand prize, right? And then there's the 5 small prizes. So that gives you a total of 6 possible prizes you could win. So you have 6 ways to win, or six different ways that you can walk out of there with a prize, and there's 200 entrants, right? So your probability went up to 6 out of 200. And then what's the probability that you don't win anything? Well, that's the complement of winning something, right? So these two here are complements. Whoa, I didn't want that. They're complements, right? So what that means, there's 6 ways you can win. That means there's 194 ways you can't. And so this probability is 194 over 200. And if you notice, the probability of A bar equals 1 minus the probability of A. More specifically, these two things add up to 1. So there's a couple of other ways to approximate probabilities. And the first one is the relative frequency approach. And this is used quite often. And so the idea is this: if you want the probability that an event A will occur the next time, then what you do is you look at the number of times A has occurred in the past over the total number of times the trial has been conducted. For example, if you have Shaquille O'Neal steps up to the free throw line, and you look historically at his success rate, how many he's made. So he's made 5,750 out of his last 10,895 free throws. Based on this data, estimates, and again, this is an estimation, the probability that he makes his next free throw. So that's just the number of times he's made it in the past over the total number of times he's tried. That's 0.528. For the your turn problem, we have 200 people walk by your store over the past hour. 15 of them have entered your store. You want to estimate the probability that the next person coming down the street will walk into your store. Now, we don't know exactly what that probability is, but we sort of look back at our relative frequency of the past hour, and we see that in the past hour, 15 out of 200 people came into the store. So the estimate that the next person coming down the street will enter your store is 15 over 200, 0.075. The law of large numbers basically says that this relative frequency approach right here, it says that as the procedure is repeated again and again, like the more times the trial is repeated, such as throwing a free throw or counting people who walk by your store, the more often that's repeated, the relative frequency probability gets closer to the actual probability. Right? We don't really know what it is, but we know we're getting closer as the number of trials increases. The round-off rule is probably best to give these as fractions if they're simple. 1/2 is nice and simple, 2/3. But if you get into something strange with a denominator that's, say, bigger than 10, if you have, say, something like 6 over 13, you're probably going to want to write that as a decimal. Right? And so when you do that, there's convention for probabilities. And that's going to be to round your answer to 3 significant digits. And the way you count significant digits is you start for a number between 0 and 1. You start at the decimal. Actually, you just start on the left, right? you go left to right, and as soon as you hit your first non-zero, you start counting. Right. So in this case, I start counting at the 4. So 1, 2. There's 3 significant digits. A 0 counts. So 0.403 still has 3 significant digits. Going from left to right, I don't hit a non-zero term until this 4. So this is actually also 3 significant digits. Notice it's actually 4 decimals. So the number of decimals and the significant digits are not always the same. Going left to right here, you don't start hitting a non-zero until the 3rd decimal. So this 3 significant digit is actually 5 decimal places. And again, going left to right, you don't start counting until you hit that 4. And then you include the next 2 zeros because the zeros count. Okay, so that's round off. Subjective probabilities is just more of a estimate based on some information you have, and it's subjective, meaning you don't really have any scientific background for it. So, example of that is Beth estimates that a 90% chance she will complete her work in time to go to the party. What she's probably saying is, I'm pretty sure I can get done before the party, right? The 90% might just be a way of saying that. Based on homework, I estimate that you have a 30% chance of passing the test. All that's saying is, I don't think you're going to pass the test, or you don't have a very good chance of passing the test. Where things like this 30% come up, it's tricky to make that sort of estimate. Okay, so that's subjective, and that's about the end of subjective probabilities. We'll see. We'll do these paradoxes. They're kind of fun. They aren't completely necessary. It just shows you how probabilities can get a little tricky. So here's the idea. You meet a father of 2 children. Or this is the first one. There's actually 2 here, right? You meet a father of 2 children in the park, but you can't see his children, right? You don't know whose kids are his. And he tells you that one of his children is a boy. What is the probability the other child is a girl? Right? And what you'd think is, there's this other child. It's either a boy or girl, so you'd sort of guess at 50-50. But if you go back and you look at the sample space for this father in the park, there's 4 different things that could have happened as far as his 2 children. You could have had a boy and a boy. You could have had a boy then a girl. You could have had a girl then a boy. And a girl then a girl. This is very much like the heads, tails, tails, heads scenario. But if you look at this, if he tells you one of his children is a boy, then this one is out. And when you look at what's left, you have boy, 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 girl, girl, boy. What is the probability that the other child is a girl? Well, that happens in 2 different ways. And there's a total of 3 outcomes, so it's 2/3. Right. So it's not 1/2. If you thought it was 1/2, that intuitively that sort of makes sense. But from the classical approach of probability, there's actually a better chance that the other child is a daughter. If, on the other hand, he tells you that the oldest child is a boy, now what is the probability? He just changes the sentence a little bit. Now what is the probability that the younger child is a girl? Now all of a sudden you're talking about a specific child, the younger child, and your intuition should serve you correctly, and we get 1/2, and here's why. If you look at our sample space up here, right, we know that the oldest child is a boy, so this is certainly out, and then this is certainly out because that's the girl is the oldest child. So now you're down to 2, right? You have boy, boy, and boy, girl. Right? And so now what's the probability that the other sibling is a girl? Well, it's 1 out of 2. My sample space is 2. 1/2. Right? So the paradox is, it doesn't seem like him telling you that the oldest child is a boy or one of the children is a boy should change things, but it does. Here's the Monty Hall paradox. I'll draw you a little picture of this. So the way this goes is, in the game show, there's 3 doors. Door number 1, door number 2, door number 3. And behind one of these doors, there's a car. So there's one car, and there's 2 goats. And we'll make the assumption that you want the car. If you really want a goat, then you're in luck, because this game's going to really work out for you. Okay, so you pick a door, and let's just say for the, we'll just say you pick door number 1. So you pick that one. Number 1. So the probability that you get the car is equal to 1/3. There's a 1/3 probability that the car is in there, right? And then the probability that the car is in one of these 2 is actually 2/3, right? So that's how it starts off. There's a 1/3 chance you won, and a 2/3 chance you didn't. But then he knows where the goats and the cars are. The car is. And so one of these 2 here is certainly going to have a goat, right? Because there's only one car. So suppose he opens up this door, says it's not in there, there's a goat. And then he asks you, do you want to switch your bet? Do you want to switch your door? Would you rather switch over to door 3? And the question says, the question asks, should you switch? And the answer is yes. You should always switch under these circumstances. And here's why. There's a there's a 2/3 chance that the car is over here once the game started. And he opened one of them, but that doesn't change the 2/3 chance. You still have the 2/3 chance that the car is over here. So you might as well switch and get the increased probability. And here's another way to see this. It's harder to tell because there's only 2 things there. You think, it's 50-50. It's a little harder to tell, but if you suppose you had 100 doors, right? And I won't get you with a whole bunch of these. All right, all the way down. So there's door 1, 2, 3. Say this is door 72, 73, 74, door 99, and 100. If there was 100 of these doors, he said, all right, pick a door. And you picked door number 1. So you pick this one. And then he knows where the car is, knows where all the goats are. So suppose he starts opening doors. And he opens door number 2. It's not in there. Door 3, not in there. Opening. No car. 72, not in there. He skips 73 and goes to 74. Not in there. 75, 76, 77, all the way up 99, 100. So he has crossed out 98 doors, or opened 98 doors to reveal 98 goats, right? Now there's a 1 in 100 chance that you picked the right door. And so the car is most likely sitting right there. That's why he didn't open door 73. Right? So if you switch, you have a 99 out of 100 chance of getting that car. If you don't, you have a 1 in 100. And this sort of helps make the picture, it makes it a little more obvious. Because you look at that and you're like, why didn't he pick 73? And the reason is because the car is back there. But it's harder to tell in the 3-door scenario. It seems like a 50-50, but it's not. You should always switch and take advantage of that improved probability of winning. Alright, so that's the introduction along with some a couple paradoxes that I just sort of find amusing. And we will catch up with you in chapter 4.1. Alright.